Okay, this next part, this is where, that last part, a lot of conceptual stuff. Now we're going to get into the nuts and bolts of this a little bit. We're going to start talking about inductors, okay? Now, the great thing about this can be combined with an AC circuit and really do some awesome stuff. If you start taking this magnet here and you start spinning it, that's AC current right there. Or you find a way to drive this in and out, AC current. Now, the real advantage of AC current, of course, are what are called transformers. Now, I say of course because some of you might have heard of this story or whatever, but essentially what a transformer does is that it allows you to keep the voltage pretty high. DC current, you can't do that. And we probably won't talk about that this year because AC current's not on the exam, but maybe at the end of the year we could talk about that a little bit. All right, now, first thing I want you to do is read, yes, read sections 30-5 and 30-6. Okay, now, what we talked about with that, I'm just going to say very briefly on 30-6, is that we said that there was an EMF produced when we had negative dpb dt. Okay. Now, if I expand that, remember voltage. We talked about the voltage through a particular electric field, and we could say that this was equal to E dot ds. This is your voltage. I think it's negative. And we have the negative up front there, so they cancel out. Okay, E dot ds. So now, and this is for a closed loop, and that will equal negative dpb dt. Okay, how important is this? This is one of the foundations upon which James Clerk Maxwell was able to come up with his 4 equations that basically describe everything in electromagnetism. So I'm just going to leave it there. This is just sort of the formalized description of Faraday's law, with a little lens thrown in there as well. Now,
Brenna Ling, if you're in the building, please come to the main office. Brenna Ling, to the main office.
So now, yes, I want you to read sections 30-5 and 30-6, especially when you start talking about the induction and energy transfers. That's very important. Eddy currents, very good for conceptual type questions, possible multiple choice type things. And then I want you to look at the reformulation of Faraday's law and electric potential. Now, we're going to jump ahead to inductors and inductance. Okay? Now, what a capacitor does, okay, it uses the electric field, and we use parallel plates typically. Now, we're going to take a look at the simplest way to look at a magnetic field that would go inside a coil of wire. We're going to take a coil of wire, which if we take a coil of wire and we just spin it around here, okay, and especially if I put something in here to, kind of hold those coils in place, that is a solenoid, okay? Now, we're going to talk about the inductance of a solenoid. This inductor, or a parallel plate capacitor, what it did, and I'll just put it right up on top of here, okay, what a parallel plate capacitor did was take charge to make an electric field that would affect current. Well, here I'm going to take current to create a magnetic field, which in turn will affect the current. So you need current to affect current. All right. Now, we're going to come up with a term here. It's going to be, this was, remember, capacitance was equal to epsilon naught A over D. And what was beautiful about that was that it only depended upon the geometry. Okay. You have epsilon naught, which is a constant, the area between the area of each plate and the distance between them. Had nothing to do with anything with the circuit whatsoever. Well, at first glance, inductance doesn't appear to be quite so neat. We'll take a look here. okay, we have this quantity called inductance. It's N phi B over I, okay? N is very important because it's the number of coils. We have to have, you know, a number of coils. I guess you could have one. You wouldn't have a very good inductor, but you would have, you could do that, I suppose. Now, the N is number of turns. Phi B, okay, is the magnetic flux. Now, each coil of wire, okay, creates its own magnetic flux that kind of links together with the other one, okay? It's called magnetic flux linkage. So now, N phi B, this term right here, is magnetic flux linkage. So we say that the inductance is magnetic flux linkage per unit of current, okay? That is not terribly instructive. Like when I was reading that, I'm like, okay, magnetic flux linkage per unit current. Okay, that's great. We really have to get into this and start doing some problems so we can see how this works. All right, now we should take a look at the units here. This was, remember, units of capacitance. Okay, this was farads, okay, which we designated with capital F. Okay, now, interesting enough because Faraday worked on these. Well, he worked on both, really. Unit of inductance, okay, phi B, remember that's Tesla meter squared per ampere, okay. Now, it makes sense. Name this after somebody famous, semi-famous, Henry, with the capital H, after an American scientist named, with the last name Henry, who did a lot of the same stuff that Faraday did, but Faraday got the law named after him. Henry got a unit named after him. I think Faraday made out a little bit better. Anyway, all right, so now let's start taking a look at how one of these works, okay? So now, let's just think about this. I have current that's coming down. I'm going to have introduce current, okay, through here. And the current's going to come around, down and around. Come around, like this, down and around. Okay. And I'm not going to do it for each and every coil, but just a few. Okay, so you can see how the current goes around this coil. Now, what's happening here, when current's going around this wire here, the magnetic field is going to point down. There's a magnetic field that's pointed down in here. By the way, it's not because the current's going down. If I'd spun this the other way, okay, if I wound these in the opposite direction, which maybe according to your perspective here, you're seeing that, but magnetic field can definitely go up. It just depends on how the coils are wrapped. Okay, so now, let's take a look at what the inductance for this would be. The inductance is equal to N phi B over I, okay? And we're going to look at that in terms of, and we want to look at this near the middle, okay? So it's going to be the number of turns per unit length times the length. Okay. That's big N. Phi B is BA.
Brenna Lane is in the building.
Current is still I.
Brenna Lane to the main office.
So now my inductance, and notice I have to use a lowercase l here because I'm using capital L here for inductance. Why it's L, I don't know. But the magnetic field for this coil wire, which we worked out in the last chapter, and go back and do those problems, okay? Magnetic field was mu naught I times little n. Mu naught I times little n. So I've got still NL. Magnetic field was mu naught I times little n. That's B times the area. Now the area, by the way, is the cross-sectional area here. So you could think of it, if that's really a true coil, it would be like the area of the circle that, like if you had like a light bulb up here and you're seeing the shadow, give you the area of the shadow there, divided by I. Aha. Remember I said This depends just on geometry. This, well, it doesn't appear to depend just on geometry. It's got that current sticking there. It's got magnetic field all there. So now let's just take a look here. I's are going to drop. L is going to equal n squared. Well, I just put mu naught in front. Usually you get your fundamental constants up front. U naught n squared L times A. Make sure I didn't forget something there. Yeah, mu naught n squared L times A. The inductance for a solenoid here, now it depends just on geometry. N is the turns per unit length. L is the length of the solenoid. A is the area of the solenoid. Okay? It's just the geometry of the solenoid. Now, we're not going to look at other types of inductors. This is our inductor. We're not going to look at inductance of toroids or anything else like that. That's a little bit different. Okay? But that is going to be, now your book calls it the inductance per unit length.
Mr. Dooley, please call 1205.
Okay. Which I'm just going to leave that alone for right now. You can do that as the inductance per unit length if you so desire. Now, I'm going to take this through section 38, and then I'm going to look at RL circuits separately. Okay. So now, I have self-induction. Okay. Now, if I look at this here, going back up to that one, if I have a current that's going through a wire here, now I'm going to do it like this. Okay? Current's going to flow like this. Now, I turn the current on, it's nothing initially. Okay? But now, there will be a current induced back in the opposite direction. Just to try to, the net current's still going to be going forward, but there's going to be a current that tries to, there's going to be a force trying to push it back the other way. Okay, I like to think of it as the net current is still going in that one direction, but there's like a, when you induce a current, there's a current that tries to fight back. Ultimately loses, but still has a current that's trying to fight back. So now, let's just say that as this comes around here, okay, it's going to go around, down, okay. So now, this current, okay, as it wraps around, and it depends again on the perspective of this. Okay, I'm saying that this is the front, and it's hard to see. Okay, it's going to swing around like this. So as that wraps around, okay, magnetic field is produced in that direction. Okay. Now, if all of a sudden I put I starting to go up, okay, current is increasing, that would mean that there'd be a magnetic field that's increasing going down, running through the center of these coils. They don't want that change. So what happens is, to try to fight that, okay, and you can look at this on page 806 of your book. Okay. Now, okay. So now, in order, if I have an increasing I here, I'm going to try to create a voltage that tries to push back in the other direction. So if I is increasing in this way, that means that V has to be increasing that way. So I have to induce voltage in that direction. Okay, that's going to try to slow the amount of the rate at which that current is increasing. Okay, same is true if I have now I decreasing. Okay, and you guys can look in your book at this. If I is decreasing, okay, now the magnetic field inside here is getting weaker. In order to compensate for that, additional current tries to make up for it, and you get a induced voltage that points down. So now, putting this together, if I look at this here and this here, where I have L is equal to N phi B over I, and I just rearrange to N phi B times Li. Now, again, the EMF that's produced here will equal negative N dpb dt. Just as, and you pull the N out because the N is not changing, the number of turns. L is not going to change, so that will be a constant. So if I was going to do that, I could say that my induced EMF here, it would equal negative L di dt. So the voltage across an inductor is negative L di dt. Negative L di dt. After a long period of time with the capacitor, after a long period of time with the capacitor, it reaches steady state. And the current comes to a straight value. Think about this. The voltage across an inductor, if it reaches steady state, it means that you have a constant current. If I have a constant current, what does this vanish to? 0. The voltage across an inductor, when we start looking at these RL circuits, that voltage across the inductor is going to disappear to 0. Whereas with a capacitor, it increased to match whatever the battery was. This will start off at about what the battery is, and drop off to 0 if I just put this in with in series with the resistor and inductor. So this is going to be important, and we're going to talk about RL circuits next. And we'll get into that, and we'll close it up. Again, read sections 30.-5 and 30-6. The reason why you're reading it, I want to go home. It's Friday on spring break, for crying out loud. I want to go home just as much as you guys want to get out of here.